Okay. So you can see my screen, right?
Yes, sir.
Yes, sir.
Okay, so in the last lecture we introduced vector space, some definitions. Like today we'll start. Or my aim in today's class is to cover basis and dimension at least. So let us start today's lecture. So today is lecture 6, and the date is 26. All right. So let us start. So in the last lecture, some of you asked me whether, so in system of linear equations we proved that if we have equivalent systems, then they have the same solutions. Then some of you ask, what about the converse? That means if we have systems which have exactly the same solution, then can we say that they are equivalent? So for example, you can, so the answer is yes, you can do that, but the proof is not that straightforward. The proof is much more involved. So I can give you the hints because otherwise it will take more time. And if any of you is interested, and if you are not able to get it, then I can prove it later on, or maybe I can give you some, let's say, uh, some personal time out of this lecture time, and then we can discuss. So the idea is that if suppose, so this is just something, some discussion from the last lecture. So what we want to prove, so we want to prove that if, so this is what we want to prove, this is a, so let's say if we have two system of equation, homogeneous equation, ax equal to 0 and bx equal to 0, then they, and suppose that they have say exactly the same solution, then our claim is to show that A and B are equivalent. Okay. So as I said, the proof is not that straightforward, but I can give you the idea. So there are two ways to prove this. First, you observe that they have exactly the same solution. That means their solution space is same. That means if I, let's say, if I say, let's say S1 is the solution space for first one. That means it's the collection of all x such that ax equal to 0, and S2 is the collection of solution space of is collection of all solutions of bx equal to 0. Okay. Then what does it mean? What does it mean? So it means that rank of, so it means that we have the same number of free variables in the system ax equal to 0 and bx equal to 0. So that implies that we have the same number of leading variables. So that means rank of, so S1, since we have S1 equal to S2 by the given condition, this implies that rank of A is equal to rank of B. So this is from the given condition that they have the same solution. Now using this, you can prove that by using this fact, you can prove that A and B are equivalent. So there are two ways to prove this. I can give you both the ideas, but you can complete the proof. So the first idea, which involves some more terminology, which we have not introduced yet, and when we will introduce this row space and range space of a matrix, then we will prove it. Then using this idea, one can prove this easily. So for example, if you show that, so although I have not done this, I mean I have not introduced null space and range space, so it is just an idea. So whenever we will introduce this notation, we will we can prove this. So the first idea is that you show null space of A is equal to same as row space of A orthogonal complement. Okay, so this thing I have not introduced, but I'm just giving you some idea that whenever we'll cover these topics, then we can come back and we can prove this. So using this result or using this statement here, one can show that uh, the the row reduced echelon form of A is same as row reduced echelon form of B. So if they have the same row reduced echelon form, that means there is a way to go from A to its row equivalent form, and there is a way to go from B to its row equivalent form using a finite number of elementary operation. So one can say that they are equivalent, right? So proving that they have the same row reduced echelon form is equivalent to saying that they are equivalent. So we are done here. So the idea one is that using this fact you show that row reduced echelon form of A and B are same. These two things. Idea two is that you independently prove just by whatever information you have so far about the system of linear equation. Using that you prove that row reduced echelon form of A is same as row reduced echelon form of B. Okay, so using this, so there are cases you have to consider. So you keep in mind that rank of A is equal to rank of B, and then you assume that suppose row reduced echelon form of A is not equal to row reduced echelon form of B. Then what happens? Then either the leading variable in some row, the leading variable is not same, they are not occurring at the same position or in the same column in both the echelon forms, or leading variables are occurring at the same position, but the free variables are not occurring at the same position in these two forms. Then what happens? So you consider this, and then you convince yourself that this cannot happen, and therefore row reduced echelon form of A is same as row reduced echelon form of B, and using this you can prove that, and this implies that A and B are equivalent. Okay, so you can start this convincing yourself by taking a 2 by 2 example. So let's say Ax equal to 0 and Bx equal to 0 when A and B are both 2 cross 2 matrices. So 2 by 2 systems two equation in two unknowns. You can do it for this system, for 2 by 2 system, and then you can prove it for general. Okay, so this is the idea. Okay, so you work out this idea. So let's move to
Sir,
yes.
sir, if the solution set is going to be empty,
Is the same
that
solution? Solution set is never be, because 0 is always there.
okay, sir, it is homogeneous. Okay, sir.
No, but the same idea you can use for non-homogeneous also. If it is empty, then it would be empty for both the sets. I mean both the systems. Okay.
And then that will also imply that A and B are equivalent matrix.
So then it is like trivially. So I mean they are empty sets. So like, so you when you say that they have the same solution, then you can assume that, okay, that there are solution.
Okay, sir.
So if both the systems are so if A is inconsistent and they are equivalent, then B would also be inconsistent because they have exactly the same. So otherwise it would be a contradiction of the result which we have proved that equivalent systems have the same solution.
So,
Yeah.
सर जैसे कि एक मैट्रिक्स ए है उसमें नंबर ऑफ अननोन्स तो नंबर ऑफ मतलब मैट्रिक्स बी में जितने नंबर ऑफ अननोन्स है उसके इक्वल है, बट अगर नंबर ऑफ इक्वेशंस डिफर कर रही तो फिर क्योंकि सॉल्यूशन सेट तो फिर भी सेम हो सकता है ना, तो हाउ कैन इट बी इक्विवेलेंट?
So you are saying for non-homogeneous system?
नो सर, होमोजेनियस सिस्टम में ही मतलब अगर नंबर ऑफ इक्वेशन
Number of equation?
of A is not equals to number of equation
No,
of B.
so when you are proving this, you assume that A and B have the same size. So that is
then yeah, then okay.
yeah. So we assume that A and B are of the same size. So when I say that these solution space are same, what does it mean? Like, it cannot happen, na? Otherwise, like how would you say that this S1 is equal to
Sir,
S2?
it will happen ना actually जब number of unknowns सेम होंगे और तो सॉल्यूशन स्पेस सेम हो सकते हैं.
हाँ?
नंबर ऑफ अननोन्स जब सेम होंगे दोनों सिस्टम में तो सॉल्यूशन
Yes,
सेट सेम हो सकते हैं.
yes, yes. So here we are assuming that A and B have the same size. Okay, so let's move to today's lecture. So we start by introducing linear combination. So what is a linear combination? Right. Okay. So a vector, let me define this first. A vector V in a vector space V over F is called a linear combination of vectors, let's say V1 to Vk in V, if V can be written as this sum alpha 1 V1 plus alpha 2 V2 and so on up to alpha k Vk for some alpha 1 to alpha k in F. Okay. So if a vector V is can be written in this form alpha 1 V1 plus alpha 2 V2 and so on up to alpha k Vk, where alpha i's are coming from the field, then we say that V is a linear combination of vectors V1 to Vk. Okay. Then using this we can define span of a set. So what is span of a set? So suppose that we have a subset of a vector space V. So this is a subset. Okay. Then span of S. Can you tell me what is span of S?
Set of all linear combination.
Set of all linear combination. So can you tell me what it would be? Linear combination
of vectors of
Linear combination of the vectors
S.
of S.
that this kind of thing you are saying?
Alpha bi belongs to S.
I1 to N.
Bi belongs to S.
So it must be
Vi belongs
finite.
to S.
Must yeah. So when you say span of S, it is the collection of all finite linear combination of vectors from S.
I
Okay,
goes
so
to 1 to N होगा ना.
yes, yeah, I know. So whenever we say span of S, it is always finite linear combination of vectors from S. So that means this N belongs to N. You can take all the linear combination, or you say finite linear combination of vectors from S. Okay. Now by convention, this is true. So I'm defining it for any subset. So empty set is also a subset. So for convention, we use span of an empty set. So this is an empty set. So sometimes we also use this notation phi for the empty set. So this is equal to 0. This is the convention we use to make it complete. This is just for convention. and if span of S and if span of S is equal to V, that means the complete vector space, then this S is called
Spanning set.
spanning set of, and in this case
V.
we also say that S spans V. Okay, it's the same thing. Okay, fine. Now you can easily prove that whether S is a subspace or not, span of S
Sir, you are not audible.
Yes, sir, you're not audible.
Hello.
Yes, sir.
Yes, so
Yes, sir, you are audible.
I'm audible now. Okay, so let me share my screen again. So can you see my screen now?
Yes, sir.
Yes, sir. Yes, sir.
Okay, fine. Okay, so we were talking about we were defining linearly dependent set. So let S be a subset of V, then S is called linearly dependent if, can you tell me what is a linearly dependent set?
If one vector of S can be written as a linear combination of other vectors of S.
Is it like is it correct?
Yes.
Anyone can be
Anyone can be written as a
in linear combination of other, then it will be.
other means all of them or what?
Non-zero vector.
No, all of them not. Some of them.
So then you have to say it properly.
Yeah.
Any scalar in the linear combination is non-zero as is called a linearly dependent set.
Any linear combination is non-zero. What do you mean by that?
So any scalar in the linear combination of any vectors
Hmm.
is called linearly dependent.
But that is not any scalar of any. So how would you check that? If you define it in this way, then how would you check? You will check for all the linear combinations?
सर आपने जो
Sir,
वो डायरेक्ट सम में जो डेफिनेशन दी थी वो भी लगा सकते हैं आप.
What
sir,
is that? So you just define whatever.
sir,
Whatever you want.
if we write linear combination of element of vectors of S, then for some scalar alpha I equals not equals to 0, then it is called linearly dependent set.
But that
Sir,
is not clear. This is not.
सर अगर जीरो के लीनियर कॉम्बिनेशन में एक भी स्केलर नॉन जीरो होता है तो वो एस का जो सेट होगा वो लीनियरली डिपेंडेंट होगा.
So let's say you want to write this. So when you are saying this, I know that you know the definition, you have the
So,
idea, but you are not able to say it properly. Yeah.
so
There is-
if we write a vector in the form of ci and ci into vi, where vi is coming from s and ci is coming from any scalar, and if we want s particular vector to be zero, then only one case is to be ci have to zero, then it will be linear dependent.
Yeah. So you are saying that at least you have one non-trivial way to write zero as a linear combination of vectors from S. This is what you are saying.
Yes, yes, sir.
So if you want to write it mathematically, then how would you write? So this
So
S is a set. S, I don't know whether
s
it is
is
finite or infinite. So then how would you write this?
so s equal to sigma ci vi,
So you are
where
saying
ci is
so CIVI, let's say CIVI, I equal to 1 to let's say M. Then
n, where vi is coming from s and ci is any scalar,
any scalar. Okay.
any non-zero scalar, I mean.
So what? So
So
you are saying that this equal to 0.
no, sir, this summation of the ci vi will be a linear combination of a particular vector.
A particular vector, but linear
Yes, sir. जिसका
so
हम
you
लोग
are
लीन उस जिस वेक्टर के लिए सर हम लोग लीनियर कॉम्बिनेशन लिख रहे हैं उससे
सर, मैं-
इक्वल होगा.
किस वेक्टर के लिए लिख रहे हैं?
सर
सर एनी वेक्टर व्हिच इज
जीरो
कमिंग
वेक्टर
फ्रॉम
के
एस.
सर ये लीनियर कॉम्बिनेशन जीरो वेक्टर के लिए लिखना होगा अगर मैं
सर,
लीनियर
मैं-
डिपेंडेंस
एनी वेक्टर व्हिच इज कमिंग फ्रॉम एस.
जीरो वेक्टर के लिए होगा आइडेंटिटी
So you
मैट्रिक्स.
are one is saying V, one is saying 0. Any वेक्टर के लिए होगा तो 0 के लिए भी होगा. So let's say 0. फिर
यस
यस सर.
then
अगर
sir
इस
Then some
it
सी
will
आई
it will have non-trivial solution also. It will have non-trivial
Sir,
solution
it
also.
will linearly.
okay, so you see you have so many like statements for just for defining linearly dependency. Now I understand that you have the idea, but you are not able to say it, and you are not able to also say precisely what would be the mathematical expression. So see, we are given a set S, and we want to say that whether it is we want to say that it is linearly dependent. Now when you are defining something, the definition should be very precise. So let me write this and tell me whether it's a correct way to write. So I don't know. So you are saying that you take any vector and write it is a linear combination of other vectors from S, and then you are saying that when this vector is 0, then there exists at least one this non-trivial thing you are saying, not trivial linear combination. So I understand that you have this idea. So if you want to write it, then how would you write? So if there exist, let's say there exist distinct vectors. So this is important here. There exist distinct vectors v1, v2, and so on up to vk in S, and scalars alpha 1 to alpha k in F, not all zero. At least one of these scalar is not zero, and such that alpha 1 v1 plus so on up to alpha k vk is zero. So what it says that no matter what is this set S, if you are able to find at least uh, at least one k, where k is a non-negative integer, if is a positive integer, then if you are able to find v1 to vk vectors in S and scalars alpha 1 to alpha k, where not all of them are zero, at least one of them is non-zero, such that alpha 1 v1 and so on up to alpha k vk is zero, then this set is called linearly dependent. Now a set which is not linearly dependent is called linearly independent. So a set which is not linearly dependent is called linearly independent. And for this I may use this abbreviation L dot I2. Okay. Now if you want to write the negation of this statement, that means the definition of linearly dependent, what it would be? Let's say I want to define linearly independent. Now can you define linearly independent using the definition of linearly dependent? I mean, getting some idea from this definition.
Yes, sir.
Yeah, so
Sir,
tell me what it is.
Let S a subset of BF, then S is called linearly dependent if there
No, no,
exists
not dependent, linearly independent.
linearly independent if there exists non-zero BI belongs to S and and scalars alpha 1 alpha I belongs to F such that summation alpha I BI equals to 0 for all alpha I equals to 0.
So most of the thing, whatever you said, most of the things are correct. Only one thing is a problem. You said that there exist vectors v1 to vk, non-zero vectors
All
Should be
non-zero
given any
non-zero
vectors.
vectors
or any non. So
non
basically, yeah. So just one general thing. Whenever you are writing negation of a statement, so here you are trying to write a negation of a statement, then in that case, all the quantifiers are changed. For the example, there are two quantifiers, there exist and for all. Okay, these are the two universal quantifiers. So wherever there exists quantifier, in the negation it would be for all, and if there is a for all in the statement, then in the negation it would be there exist. The second thing is that
okay, sir.
all the inequalities will be reversed. Whenever you're writing the negation of a statement, if there are inequalities involved in the statement, then in the negation they will be reversed. Here we don't have any equality, but what it would be if we want to write the negation of this, uh, S is linearly independent. S is subset of V. S is linearly independent if for any set of vectors, let's say V1 to Vk in S, alpha 1 V1 and so on up to
Sir,
alpha k
non-zero
Vk,
vectors.
S is,
Sir, non-zero vectors.
so
V1,
here,
V.
yeah, just a minute, just let me finish this. Let me finish this. For any set of vectors V1 to Vk in S, alpha 1 V1 so on alpha k Vk is 0 implies alpha I equal to 0. for each I, then S is called linearly independent. So why you need S to be no, I mean these vectors to be non-zero. So if it is a zero, then it cannot be. If S contains a zero vector, then it won't be linearly independent by definition. You don't have to assume this. If a set contains a zero element, then it won't be linearly independent by definition. You don't have to assume this.
Yes, sir.
Right?
Okay, sir.
Okay, fine. And in some cases, instead of a set, we are given some vectors. Let's say v1 to vk. Okay. Then if we are given this vector v1 to vk and they are linearly independent, then we say that instead of set, we say v1 to vk are linearly independent. The vectors are linearly independent. It's just the terminology we use. So clearly what we have observed here, so let me make some observation here, some very simple. As you mentioned already, if 0 belong to S, then S is always linearly dependent. This you have already said. And what about this set? If we have a set V, if we have a non-zero vector, let's say V, from the vector space V, then what can you say about this set, singleton set V?
Linear independence.
This
Independent.
Li.
This is right. And also, suppose that we have two sets, let's say S1 and S2, and suppose that S1 is a subset of S2. Okay, and both these S1 and S2 they are subset of the vector space V.
सर सेकंड पॉइंट में सिर्फ नॉन जीरो होने पे ही एल हो जाएगा. अगर कोई दो वेक्टर एक दूसरे के मल्टीपल हो गए तो फिर वो लीनियरली डिपेंडेंट हो जाएंगे.
No, I am saying just read the statement careful. I am talking
For
about
singleton.
the singleton set.
It's a
Singleton.
single vector.
जस्ट
So it's just
ओके.
one vector. Okay. So then what can you say about S2, S1 and S2? If S1 is linearly dependent, then what would be S2?
Yes, S2 is independent.
S2 is
Linearly
एस टू
linearly
इज
dependent.
dependent.
आल्सो लीनियरली डिपेंडेंट सेट.
Dependent.
Right. And when S2 is linearly independent,
S1 is linear.
S1 is
S1 is
linearly
linearly
दिस वन इज
right,
आल्सो a linearly independent set.
right. So this is just some basic thing. Now let me define using this. What is the basis? Basis of a vector space. All right. So suppose that we have a vector space V. So this is a vector space, let's say, over the field F. Okay. And suppose that we have a subset of. So can you tell me what is the basis?
If the subset of V is Li and is spanning set, the subset is called the basis of
V.
vector space.
So then V is a basis, is called a basis. Sometimes it is also called as Hamel basis. So when we don't when we don't use this term Hamel basis, then it is normally like this definition basis. So basis or Hamel basis, this is same. That's a different name for the same thing. So in functional analysis, because there are two kind of bases, so just to differentiate them, we use this Hamel basis, and the other one is Schroeder basis. Here we will talk only about this basis, which is actually the Hamel basis. So what is this? It's B is called a basis for V if it satisfies two things, that span of B is equal to V and the set V is linearly independent. So if any set that satisfies these two properties, then it is a basis for this. Okay. Now the next result which I am going to prove tells you that whatever be your vector space, it will give us. So it is it would be the result I will prove, the next result which I'm going to prove, that gives us lot of many other results for related to basis of a vector space. Okay? So this result says, so let me first write this statement. Suppose that we have a vector space V over F. Okay. And suppose we have a subset of V which is linearly independent. And suppose we have another subset of V such that span of V span of S is equal to V. So that means S is a spanning set containing this set L. So that means L is a subset of S. Okay, this is given to us. So we have a vector space, we have a linearly independent set, and then we have a set S that spans V, and it's also contain the set S. Then using this hypothesis, then there exists a basis P of V such that L is a subset of B and B is a subset of S. Okay. Now see, suppose if we are able to prove this result. Okay. Suppose that we are able to prove this result. So I will prove this, don't worry. But let's see the consequences of this result. Okay. So what this result says? It says that if suppose we have a vector space and if we have any linearly independent set, let's say L, and if we have a spanning set S, V, such that it contains the set L, then we can always find, or there exists a basis B of V such that this L is a subset of B and B is a subset of S. Now you see here, using this result, we can prove that. So let me write the. So I will prove this result. Don't worry. But before that, using this result, you see the consequences of this result. So let me first write. Okay, as a corollary. So we'll prove it. But before that, let us assume that this result is true. Okay. So as a corollary, we obtain the following thing. Let's say. So using this, you can show that every vector space has a basis. Now you have to tell me using this result how to prove this. So I'm saying that if we have a vector space, so let's say I'm writing the corollaries of this result. So let's say we have a vector space over F. Okay. Then the first corollary of this, using this, you can say that there exists a basis of V. Now, can you tell me how to prove this using this? Can you give me some idea?
Sorry, span of V is V.
So-
So
Then there exists a basis beta of V such that V is subset of beta and beta is subset of V.
see, you want to use this result. So you are giving me a spanning
So-
set. Yeah.
Yes, sir.
There, for every vector, there is a spanning set, and when we extract all the linearly dependent vector from the spanning set, then at the end of the all collection of linearly independent vectors will form the basis for V.
So how many of you are agreeing with her?
Sir,
Yes.
if V vector space is going to be zero vector space, then that will also true.
Yes, because we know that empty set, we are saying span of phi is equal to 0.
Okay,
So
sir.
phi would be the empty set, is the linearly independent. So if there is no vector,
Then,
then by definition it is linearly independent.
answer. Okay, there is no vector,
Yeah.
then
So
by
just
definition.
let
Okay.
let me comment one thing here. So one of you said that if suppose we have a spanning set, then we can remove all the like linearly dependent set from like the vectors which can be written as a linear combination of other vectors, and then we can reduce it to a basis. Something like that you said, right?
Yes,
Yes.
sir.
But that statement, how would you do that? Let's say I give you, let's say, an infinite set. Okay, then
Yes, sir.
how would you extract this? I mean, what would be the process? Will
Yes,
this
sir.
process, yeah, will this process end?
Yes, sir. When we extract all the dependent vector, this process will end. Then we
But
can get a
how
basis.
would you know that you have extracted all the vectors?
So when
Sir,
there is no vector which is the combination of other.
But how would you prove that? I understand what you are saying, but how would you
Yes.
prove that? So can you give me a proper argument that this is how we will do? This is how we will
So
start.
by the help of Joron's lemma.
Yes, sir. John's
Infin-
lemma.
What is that? How would you use the John's lemma?
Sir, by using John's lemma, we will say that there exists a maximal Li subset in V.
Hmm.
Uh, this maximal Li subset may not span V. Then we will add some vectors in this maximal Li set, and it will span V. Then we will get the spanning set of S, and the maximal Li set will be the subset of the spanning set of V.
So see, you are doing something by adding, like let's say, like you are saying that you will say that there exists a maximal linearly independent set using the John's lemma. This is what you are saying, and then you will ultimately you are going to use this result only,
Yes, sir.
right? So
Yes,
whatever
sir.
I have written here. So because you are saying that you will take this L as a linearly independent set and you have a spanning set, let's say S, then this result will give you a basis.
Yes, sir.
So that is fine. But here also you are saying that, let's say, assume that there exists a maximal spanning set. What I'm saying that for that also you have to prove something. Now, if suppose you have this result, so I'm saying that you have a linearly independent set and you have a subset, you have a spanning set S, then you can always show that there exists a basis B that contains L, and that basis uh, is contained in S. Now, using this statement, the proof of this is very straightforward. If you want to use this, you just have to give L and S, and that's all. Now, can you give me L and S such that I can always say that okay, this this means every vector space has a basis.
Sir, any non-zero vector for L.
Any
Non-zero vector V, singleton V is L,
hmm.
and S is V.
Sir, for SV.
So you are saying that L is any, you can take any non-zero vector, but what if
Yes.
when V is, let's say, just a zero space?
sir, then you said that it is going to be phi set only.
Phi only. So you'll have to say that for zero space it is a different argument, and for non-zero space it's a different. So it's
Yes,
fine
sir.
if you say it in two different arguments, then it will fine. Otherwise, what you can do, you just take. So I can give you the hint here. So you just take L as, let's say, empty set, because I am saying that L is a linearly independent set, and by definition empty set is linearly independent. There is no vector, so it is linearly independent. It follows the definition because there is nothing to check. So empty set is linearly independent. and you take S as V, then this says, then using the previous result, you can say that there is a basis of V, right? Do you agree with me?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. So see here, using this result, it is very straightforward to prove that every vector space has a basis. We don't have to bother about other things. Now, not only this, we can say many more things, many other things. For example, let's say we have a subspace of V W, okay? And then let's say V tilde is a basis of V, because W is a vector. W is also a vector space, and we already know from the previous corollary that it will have a basis. So let's say B tilde is a basis of W. Sorry. Okay. Then we can say that there exists a basis V of V such that V tilde
B
is a
tilde is a
subset.
subset of B.
Right. Now, how would you prove again using this result? How would you prove this thing?
So take L is equal to B tilde.
So take L is equal to B tilde and what will
S
be
is
your
S equals to W.
S is equal to V.
so
And S,
again,
yes, sir, S equals to B.
so why S equal to W won't work? So some of you said that take S equal
Sir,
to W. Why it is
Sir,
not?
S
So
is equal
there
to
may be
W.
some
S,
sir,
S
elements in
equal
because
to
S
beta.
that may be not in W.
X equal to beta. S equal to beta.
S is equal to V, sir.
So see here what we want. So some of you said take S equal to beta, but beta actually we have to prove that there exists beta. We don't know this
Yes,
B. We have to
sir,
prove.
S equals to B.
So if we take S equal to V, then it satisfies all the hypothesis of the result. L is linearly independent because B tilde is a basis. So by definition, it is linearly independent in V. S is a spanning set. Then we can say that there exists a basis B containing this B tilde, and that basis is contained in S. So this is fine. Not only this, let me state some more corollaries. So all these things you have seen,
sir,
but maybe in it you have seen a different proof, or maybe you have done it for a finite set of vectors. But whatever we are doing,
sir,
we are not
if it's
assuming
then
that.
what is wrong there, sir?
Sorry.
Sir, if we are going to take S is equal to beta, then what will be wrong, sir?
Beta is not there. Now we have to show that there exists a basis B or beta, whatever. See,
Sir, then yes, sir,
wait.
beta is beta.
See what is given to us. Given is W, which is subspace, and B tilde is the basis of W. Now we have to show that there exists a B. So if you already taking B, then what is there to show? We have to show the existence of B, no?
Okay, sir. Thank you, sir.
So you are assuming something which you have to prove. So the third statement is a basis is a maximal linearly independent subset of V. Now can you prove this also using whatever information we have? So can you prove that whatever results we have proved already, can you use this idea and show that can you use these results and show that a basis is a maximal linear independent set? So what do you mean by maximal linear independent set? First you tell me what you mean by maximal, the term maximal.
So maximal means if we add any one vector from in this maximal li, then it will LD.
Yes, right. And similarly, when we say minimal set of satisfying some property means
If we remove any vector, then it is not going to satisfy that property.
right, right. Exactly. Now here we want to say that a basis is a maximal linearly independent subset of V. How would you prove this?
Sir, means if we are going to take, sir, if we are means there will be exist beta from the first condition. If we are going to take L is equal to phi and S is equal to V.
So there is a basis. Let's say there is a basis. So because we have
Yes, sir.
already shown that B there exists a basis, so you say that B be a basis.
Okay,
Now you
sir.
have to show that this is maximal linearly independent set.
And sir, if we are going to add any another vector from V else than beta, then it will be linearly dependent set.
Why?
Sir, since beta is a basis, means every vector can be generated, means every vector can be generated with help of linear combination of beta.
Right.
Yes, sir.
Right. So this way you can prove it. So since B is a basis, now if I take any vector x from, let's say, from V, then this new set B union x, that is not going to be a basis because it becomes linearly dependent, because x is can be written as a linear combination of vectors from B because B is a basis. Or in other words, you can say that we have to show that we don't know how many bases are there. We don't know at this point, but we have to show that base, whatever be the basis, that is the maximal linearly independent subset. So we cannot add any vector to this. So let's say we have a basis B, and if suppose there exists x in V such that let's say B union x is linearly independent. Suppose that there exists. So I'm proving it by contradiction. Suppose that there exists x such that B union x is linearly independent. Then what? Then we know that B is a subset of B union x, and it is a proper subset, right?
Yes, sir.
And what? And this is a subset of V because x is coming from V. B is a subset, so B union x is also subset of V. Now, this means what? This means span of B cannot be equal to V because here it is proper. So this implies a contradiction that B is a basis, right? So see here, if you write it like in mathematical way, it's very easy to say that it is a maximal linear independence. Similarly, you can show this. You can write yourself. A basis is a minimal spanning set.
Sir,
Yeah.
is the span of B not equals to V? I don't understand that.
See here, because of this result, this argument here, you are saying that B is a proper set of B union X, right? Because X is not there in B, and this is a subset of V. So clearly, span of B is a proper subset of span of B union X, which is a subset of V. So how can be span of B is equal to V? Is it okay?
सर स्पैन और स्पैन ऑफ बीटा यूनिट का इक्वल भी हो सकता है अगर प्रॉपर भी है तो
Yes, sir.
यू ऐड मतलब ऐसा एलिमेंट इसमें ऐड करें जो स्पैन बीटा में लाई कर रहा हो
No. So what I'm saying is that
So if we take the vector space as R3 or R2 and beta is the beta is a
Yes, yes.
basis, then it contradicts.
So yes, so X is in V, which is not in B.
Linear combination of the vectors presented in beta.
Which is not in B, right? So V, which is not in B. Yeah, that we should. So X is in V, but not in V. Otherwise, it would be like linearly dependent, straightforward. So X is in V, but not in B. And suppose that this is B union X is linearly independent, then it cannot happen. So you take X is in V, but not in B. Is it okay now?
Yes, sir.
Because otherwise it would be linearly dependent. So you complete this. So this is an exercise for you. All right. So similarly, you can say that now using this, that every let's say a basis, or maybe we write it in a different way. A basis of a subspace can be extended to a basis of V. So all these results are like follow from each other. So you can see that this can also be proven using the second corollary. So when I say that basis can be extended means, so a basis of a subspace can be extended means there exists a basis. So if suppose we have a, as we proved earlier, if suppose we have, what do I mean by a basis of subspace can be extended to a basis means there exists a base. So let if we have B tilde basis of subspace, let's say W, then there exists a basis B of V that contains B. So that is what I mean by saying that B can be extended to B tilde can be extended to a basis B of V. Okay. So a basis of a subspace can always be extended to a basis of. So let us prove a different result. So there are many other things. For example, you can say that if let me. So first, let me ask you, how many bases a vector space can have?
Infinite.
Infinite. Infinite.
Always.
Sir, अगर
Infinite. So if the field is finite and vector space is finite, then it can be finite. The number of bases can finite.
It depends on
Exactly. Exactly. It depends on the field. So if suppose you have a finite field, so you can take that you can take any field, let's say finite field Z2, and you take it consider this as a vector space over itself. Then it has only finite basis, only finitely many bases. Can you tell me a basis of this? Can you tell me the basis of Z2? So let's say consider V as Z2 over itself.
Singleton one.
Sorry,
sir one.
singleton one. So the basis is,
Singleton one.
Singleton one.
can you tell me any other basis?
No, sir.
So you see that it has only one basis. So if the vector space, if the field is infinite, that means it is not of characteristic 0, then it is a field of characteristic 0, then it can always have. So now can you complete the statement after looking at this example?
then it may have finite basis.
No. So now what do you want to say? How many bases a vector space can have?
If a field is infinite, then vector space can have infinite number of bases.
Yes. So every non-empty vector space over an infinite field has infinitely many bases. Okay. So what would be the argument for this? How would you prove this?
By taking scalar multiple.
By taking scalar multiple. That is one way. Yeah, that's also. But you can always use the previous result, right? This one you can take L as a, you just, because it's non-zero, take any non-zero vector V, take L as alpha V, where alpha is the non-zero scalar, and then S as V itself. Then using this result, you can say that there exists a basis containing this L. So there are infinitely many bases. All right. So let me prove now the next result. So we have seen already so many corollaries of this. So before I move forward, let me prove the result now, the main result. So let us prove that result. Proof of, we write this as main result, okay? Just to differentiate it, okay? So this is the proof of main result. Okay, so this proof we will do, we will complete this proof using John's lemma. So the proof is not difficult. If we apply John's lemma in a proper way, then this follows. So let us recall what we have. We have a vector space. Okay, so let me recall what we have. So let us use a different color. Okay. So let us recall what we have. We have a vector space. We were given a vector space over A. We have a subset of V which is linearly independent. We have a subset S of V such that span of S is equal to V and L is contained in S. Then we have to show, then what is our claim? Our claim is to show that there exists a basis B of V such that L is contained in B and B is contained in S. Okay, so this is what we are trying to prove. Okay, and to prove this, I want to use the John's lemma. So in order to, can you recall what is John's lemma? Can you recall what is the John's lemma?
Yes, sir. If every totally ordered set of a partially ordered set has maximal L, has bound,
Your voice
Has
is not.
upper bound.
has
Has
upper
upper
bound,
bound.
then it must have a maximal element.
Maximal limit.
Yeah. So if we have a non-empty poset, that means partially ordered set, and if every totally ordered set has an upper bound in poset, then the poset has a maximal element. So in order to use this John's lemma, we first need to form a poset. Okay. So let us. So the proof is a bit constructive. It's not that difficult, but the standard proof. So I'll complete this. So assume that. So the proof is here. Let me define this set. Let's say script E. This is the set. What is this? This is the collection of all linearly independent set E of V such that, so E is, so what is this collection? This is the collection of all linearly independent set of V such that E contains L and E is contained in S. Okay. So E is linearly independent and L is contained in E and E is contained in S. All right. Then can you tell me whether this set is non-empty or what? Can you say that this set, this new
Yes, sir.
set,
Phi is subset of this.
phi?
L is subset of P.
Why phi is not subset of this?
Phi is subset
The
of E.
spanning set is sir, because it's spanning set.
So the spanning set.
Sir, L belongs to E.
L belongs to E, and therefore you cannot say that phi belongs to this script E, because this L may be non-zero, na? It's non-empty. Sorry. So why this E is non-empty? This new set is non-empty because. Can you tell me again why it is not?
Then E can be non-empty.
So why is
So
no E
if
non-empty?
if we take if we take L as an empty set, then
It contains.
phi is a subset of E, proper
No.
subset,
So see,
not equals to phi.
but I am
So,
saying that whatever you are saying, we are proving this result for any linearly independent set, not for
yes.
empty L. So
So
whatever we
since
say, that should be for every L. Yes.
so since we are given that L exists, then L can be equal to L. We have given that in the equation.
So you are saying that L belongs to this set, right?
Yes, sir.
Yes. So this is non-empty because since L belongs to this set, because L is subset of itself, so L belongs to. Okay. Now, so we have a set, we have a non-empty set here. Now, if I consider this inclusion
Sir, but
relation,
L can be possible phi. L can.
L can be phi. That is fine. But here we are proving a result. You see it. What is the hypothesis? It says that V is a vector space and L is linearly independent set. I'm not saying
Yes,
that
sir.
L is an empty set. So whatever argument I give, that should be true for any linearly independent set, right?
Okay, sir.
So if you just say that L is like this empty set is an element of this, then L has to be. This is true only L is empty, right? But when L is not empty, then this argument will not work.
So,
Okay. Now consider the inclusion relation on this set. So consider this thing with the inclusion relation. Okay. So this is the inclusion relation. What do I mean by inclusion relation? That means two E1 and E2, they are related. So that means E1, E2 are related if E1 is a subset of E2. So this is what I mean by inclusion relation. Now you can clearly check that this is a partial order relation on this script. Okay, so you can verify that this is a poset. So we have a poset. Now if I want to use John's lemma, then I have to show that every uh, totally ordered set has an upper bound in this E. Every totally ordered subset of this poset has an upper bound. So I have to prove this for every totally ordered set. So let us start with any. So let F be a totally ordered set of this poset. Okay. Now I have, so this is a totally ordered list. every two every two every two elements in this F are comparable. That means they are related. Now I have to show that this totally ordered set F has a has an upper bound. So what I will do, so let us consider this. So let K be the union of all uh, elements in F. So what is this? This is the union of all members of F. Is it okay? So you just take K as the union of all members of F. So, but the members of F are sets. So you just take the union of all these sets. Now I will show that this K belongs to this K is an upper bound for this F. Okay. Now if I want to show that K is an upper bound for this F, that means I have to show that this K belongs to this script E. So first I will show that this uh, so what I will show, so my claim now is to show that this K belongs to E. Now if I want to show that K belongs to E, then I have to check two things, that L is a subset of K and K is a subset of S. And the second thing, that K is linearly independent. I have to check these two things, right? Can you hear me?
Yes, sir.
Yes,
Yes,
sir.
sir.
Sir,
Okay.
sir,
Yes.
sir, as you've defined the poset, means we have given L and
We are given.
means we have L as a means linearly independent set. We have a given. Sir, can you little bit slide up? Yes, sir. Yes, sir. Yes, sir. Sir,
So
means suppose that if now that there can be possibility that L is linearly independent set and L is strictly containing E1 and also containing E2,
so
and E1 union E2 is not linearly independent set.
even union E2 is not.
Linearly independent set.
So
And sir, in last you've taken that all the union is going to be linearly independent in downside, sir.
see, first you tell me that this is a poset or not. Here, this is a poset or not.
Yes, sir. This is
Yes,
poset.
sir. Yes,
This
sir.
is poset. Now,
Yes,
if
sir.
I is a poset, I'm taking a totally ordered set. Totally ordered
Means you have
means
to. Okay, sir.
every two elements are related.
Okay, sir. Got it. Got it, sir. Thank you, sir.
Now, I'm taking the union of the members of this totally ordered set, not the poset.
Okay, sir. Got it.
Okay. So if you take F totally ordered set, then take union of all the members of F and call it K. Now I'll show that this K belongs to this E. Now, in order to say this that K belongs to E, I have to check two things, this and this. Now the first thing is very straightforward. Now can you tell me why this is true? This one?
So because L is a subset of E and K belong to E.
No, K belong to E, we have to prove. K belong to script E, we have to prove. This is our claim. So in order to prove this, we need to check these two things, right? By definition.
Sir, L is Li and K is union of all Li subsets.
Yes. So L is, so see here, K is the union of all E where E belongs to F, and F is a subset of this E. So L is a subset of each of these E here, right? and K is the union. So L is clearly a subset of K. Now why K is subset of S?
So it may be L doesn't belong
It may be,
to
yes. See here,
Yes,
the
L is
L may
S
be
is of S.
L.
As it is spanning set.
So this
So
this
with the
is fine,
same
no?
argument, we can say that K is subset of S.
Right, right. Because each of these subsets E here in the union, they are contained in S. So their union would also contain in S. So if all the subsets are contained in S here in the union, so if you take look at the union, that will also contain in S. So very straightforward. So this thing is, this inclusion property is following. Now we just have to show whether K is linearly independent or not. So I have to do it bit quickly, otherwise I won't be able to finish it. So I have to show that K is linearly independent. So in order to say check that K is linearly independent, what I need to do, I will take any let's say any finite collection of vectors, let's say x1 to x1 to xn in K, and then I will show that this set of vectors, this x1 to xn, they are linearly independent, and I will consider, let's say, alpha 1 x1 and so on up to alpha n xn equal to 0. Now in order to prove that this is linearly independent, I have to show that these alphas are 0 for all I, for each I. Right? Fine. Now why this is, they are linearly independent, why this is the case? Can you tell me why this is the case? Some idea? So what we have since
K is the union of all E which are linearly independent or relation is increment. तो एट लास्ट जो E आएगा सारे E एक E में इंक्लूड हो जाएंगे और वो linearly independent होगा.
right, exactly. So since what we have x1 to xn, they belong to K, right? And K is the union of all E, all I mean E, where so where K is what? K is the union of E, where E belongs to F, right? So x1 to xn, they belong to K. What does it mean? It means that there exists some E1 to, let's say, ek in the totally ordered set F, such that I don't know what are these E1 to ek, but there would be, because they are in the union, so there would be some E1 to ek in F, such that xi belong to ei. Okay, for each I equal to 1 to n, sorry, and 1 to n. Fine. Now since F is totally ordered means every two elements are comparable in F. So what does it mean? It means that if you take any two members, the members are sets. So if you take any sets, let's say E1, E2 in F, then either E1 is contained in E2 or E2 is contained in E1. So this is true for all the members of F, because F is totally ordered. So since F is totally ordered, this implies that there exists J in 1 to n, such that for some J, all these vectors x1 to xn, they belong to Ej, such that x1 to xn, they belong to Ej. Is it okay here up to this? If you have any doubt, you can ask.
So
Okay.
last two lines, since say F is totally ordered. So please again explain.
So see here, we have to prove that this is linearly independent. Linearly independent means I have to show this thing by definition. Now x1 to xn, they belong to K, right? They belong to K means what? There exists some E1 to En, because K is the union of this members of Fi, members of F. So
Yes, sir.
K x1 to xn belong to K means this xi's belong to some set of F. So I'm calling that, let's say, E1 to En, some set, right? Now, since F is
Yes, sir.
totally ordered, that means every two elements are relatable, are comparable in F, and elements of F are like these sets. So if I take any two sets in F, then either that one set is contained in another, or the other set is contained in the first one. So this implies that what? Xi belong to Ei for each I, and this set Ei would be contained in some other, let's say some Ek. So that means this Xi belong to that. So if you use this fact that they are totally F is totally ordered, using this you can show that there would be at least one J, because they are comparable. So at least one, there would be one J such that all the other sets are contained in that J. So that means what? That means
Yes, sir.
that all these
Yes.
set, all these x1 to xn, they belong to EJ.
Yes, sir.
Now this implies since all these vectors belong to EJ and EJ is linearly independent, and therefore this implies that x1 to xn, they are linearly independent since EJ is linearly independent, right? So this implies that K belongs to this set. Now K belongs to this set E. Now can you say that this K is an upper bound for F? Can you say this now? So what
Yes,
is
sir.
the, yes?
Yes, sir.
So just use the definition of upper bound. So this implies that K is an upper bound for F in this. And but we started with any totally ordered set F. So we can say using this that every totally ordered set in this poset has an upper bound. So what does that mean? It means that by John's lemma, this set E has a maximal element. So thus, by John's lemma, this set E has a maximal element. So let's call this maximal element, say, B. Okay. Now we will show that this maximal element is actually the basis B. So we will show that this is, so we'll show, if we show that this is a basis, then we are done, right? So this belongs to E. So what is our claim? Our claim is to show that B is a basis. So clearly, so maybe before this, first you observe that since this has a maximal element, what does it mean? It means that this B belongs to epsilon. B is in B. So B belongs to E. Does it mean what does it mean? It means that B is linearly independent by definition, and B contains L and is contained in S. Now, what we are trying to show, we are trying to prove here. If you look at the statement, we need to show that there is a basis B of B such that this is true. Now we already have, now what we have so far, we have a linearly independent set B. So far what we have a linearly independent set B of V that satisfies this thing. This is what we have so far. So in order to prove the claim, we just show that span of B is V. That means B become a basis. Okay, so we'll show that. So our claim is to show now that span of B is equal to V, and we are done. If we show that span of B is equal to V, then we are done. Then B is a basis and it contains N and it is contained in S. You agree with me? So we just have to show that span of B is equal to V.
Yes, sir.
Yes.
Yes, sir.
Okay, fine. Now, in order to show that span of B is equal to V, clearly what we have, so you see here, B is a subset of S, right? So observe that B is a subset of S. What does it mean? This implies that span of B is subset of span of S. You agree with this?
Yes,
And
sir.
span of S is equal to V. So this implies that one side inclusion is straightforward. Span of B is contained in V. We just have to show that V is contained in span of V, right? Or you can say,
What you have said in last, sir, last sentence of yours?
here B is subset of S, right? So this implies span of B is subset of span of S. But we are given that span of S is actually V. So this implies that span of B is subset of V,
Sir.
right? So, and we have
Yes,
to
sir.
prove that span of B is actually equal to V. So we have to show the other inclusion. That means V is subset of span of B. So we have to show that V is subset of span of. If we show this, then we can say that B is a basis. Now V is subset of span of B. In order to show that, I will show that S is subset of span of B. So it is enough to show that S is subset of span of B. Why this is? Because if S is subset of span of V, then span of S is also subset of span of V. But span of S is actually V. So if we prove that S is subset of span of V, then we are done. Right? So let us suppose, so I have 2 minutes, so I will just quickly give you argument. I won't continue this in the next lecture. You can complete the proof. So we just have to prove that S is a subset of span of B. So suppose that this is not the case. So let us suppose that there exists X in S, but X is not in span of B. Suppose that S is not a subset of span of B. What does it mean? This implies that B union X is linearly independent. Now, why this is true? This is an exercise for you. Then this is linearly independent. Now, this is linearly independent, and this is linearly independent, and then this implies that this B union X is in this. Again, why this is, you explore yourself. I don't have time, so I'm quickly doing this. This is linearly independent. This is linearly independent. Just use the definition of linearly independent and you'll get it. Then why this is in E, that is also very straightforward. But then since using these two things, since B is subset of B union X, the proper subset of B union X, right? And B and B union X belong to E, which is a contradiction. This is a contradiction to the maximality of B in E. Okay? And hence, therefore, whatever be your assumption that there exists X such that X is in S but X is not in span of B, this is not true, and this implies that S is subset of span of B. But then this means that B is a basis of B such that this is true. We are done. Okay, so the last part of this result I have like not explained much, but it is very straightforward because now till this point things are clear. We just have to you just have to explore this thing, which is also not that difficult. You just have to show that B union X is linearly independent, and this shows that this belongs to this set E. But since B is already in E, and now B union X is also in E, so B is properly contained in B union X. So this is a contradiction of maximality of B, that B is maximal, and therefore it cannot happen. So this implies that S is subset of span of B, but that means S is equal to the span of B is equal to V. That means B is the basis that satisfies this thing. Okay, so you complete this proof, and we can stop here now. Do you have any doubt?
Yes, sir. Thank you, sir.
Okay, so yes, fine. So we
Thank
can
you, sir.
stop here. It's time. So in the next class, we will
Thank
see
you,
some
sir.
more results on this.
Thank you, sir.
Yeah, okay.